Alright, hello class. In this video we're going to be talking about the chain rule. And this is where derivatives start getting complicated. Okay, up until this point derivatives, believe it or not, have been considered simple. You noticed I've been calling them basic rules. Okay, there's a reason for that. The chain rule is when things really start expanding. I don't want to say it gets really difficult, but in a way it does. It just gets more complicated. So what the chain rule is all about is dealing with way more complex functions. So things like instead of e to the x, trying to find that derivative, we'd be talking about something like e to the x squared plus 2x plus 5, right? Instead of just sine of x, okay, we'd be talking about sine of, let's say not the natural log, we don't have that one yet, but sine of like cosine of x squared, right? So this is more like functions within functions. How do we deal with compositions of functions? And that's really what this is all about. This is like a composition rule, right? As you can see here, I have the derivative of f of g of x, right? So how do we deal with the derivative of, say, f of g of x? Okay, so while this is fairly complicated, basically all of our rules are still the same. We just have to be really careful about how we approach them. So let's get into it. Okay, we're going to start by looking at some patterns that you may have noticed, you may not have, but you may have started putting this piece together. So let's say, we just have some function like this. Say y equals e to the 2x plus sine x. Of course, its derivative, dy by dx, is going to be 2e to the 2x plus cosine x. Okay? But let's say we now want to find the derivative of this thing squared. Okay? So there are two ways we could go about it. We could either multiply this all out, okay, and doing that I wouldn't really recommend, but it is a way to go. We could multiply it all out, or we could just use the product rule, right? E to the 2x plus sine x times e to the 2x plus sine x. Okay, so when we differentiate this y, it'll be the derivative of the first, which is 2e to the 2x plus cosine x, okay, times the second left alone, okay, plus the first function left alone times the derivative of the second, which will be e to the 2x plus cosine x. Okay, now notice that because we started with this squared, we get two of the same piece, essentially. We get 2, let me write it this way, the original, okay, then times the derivative. All right, now this might not be eliciting a pattern yet, but if instead, and though it might, so one thing I want to show is that notice how we have the 2 here, and now it's here, and this original function, this e to the 2x plus sine x, or this original piece, it's to the 1, and then we're multiplying by the derivative of that original piece. I think the pattern will become a little more clear when we look at this function e to the 2x plus sine x cubed. Okay, so here what we're doing is e to the 2x plus sine x. Now this one I definitely would not recommend expanding this out. Okay, we can just use the 3-piece product rule. All right, so we'll get e to the 2x plus sine x times itself times itself. Okay, so then when we do the product rule, remember I'm going to use some colors here. It'll be the derivative of the first, so that's going to be 2 e to the 2x plus cosine x. Okay, times the next two pieces left alone. So instead of writing them twice, I'm just going to say that that's e to the 2x plus sine x squared. Okay, then it will be plus. All right, we leave the first guy alone, but now we take the derivative of the second guy, so that will be e to the 2x plus sine x. And then the third guy we leave alone. I am writing it like this in this case just because we are differentiating the middle piece. And then for the third piece, we leave the first two alone. So I'll write that as the original inside part squared, then times the derivative of that third piece, which will be 2 e to the 2x plus, whoops, a typo there, that should be cosine x, sorry, plus cosine x. Okay, so if we were to bring these two together, we get another e to the 2x plus sine x squared. So we have three like terms here. So this comes out to be 3 times e to the 2x plus sine x squared, right, times the derivative of the inside here, 2 e to the 2x plus cosine x. Okay, so hopefully the pattern maybe is a little more clear now. This was our original function. And note, all we've done to get from here to here is we've moved the 3 down, subtracted by 1. So there's the 3 minus 1. So we've done the normal power rule. We just multiplied by the derivative of what's on the inside. Okay, so we might suspect, based on what we saw here, that if y was, let's say, e to the 2x plus sine x to the fourth, that the derivative going through the same process should be 4 e to the 2x plus sine x to the third times the derivative of the inside, 2 e to the 2x plus cosine x. Okay, and that's exactly right. If you were to go through the the product rule method for the 4-term piece, you'd get this thing. And we can keep this going. If y was this thing, let's say to the 100, y prime, going through the product rule 100 times, we'd get 100 e to the 2x plus sine x raised to the 99 times 2 e to the 2x plus cosine x. Okay, because remember what we're doing is for every piece, we're leaving 99 of them alone and taking the derivative of just one of them. But since it's a repeat, it's the same thing over and over and over and over again, okay, we can eventually add them up, and we'll have done this 100 times. So we add them up, and this is what we get. Turns out this pattern carries over to really anything. Okay? So we can approach way more complicated functions much quicker, because this is something we could have done earlier, just applying the product rule, say 100 times, but now that we have this pattern cropping up, it's going to give us a much quicker way to do way more complicated differentiations. All right, so let's talk a little bit about what this chain rule is, how it works, say when we move away from the product rule into just straight compositions. Okay, so the chain rule, even though we use the product rule to kind of introduce what we're doing or introduce the pattern, it's actually built more upon compositions. It's a lot more general than just, say, a product rule. So it's built on compositions, and what I mean by that is, so if the rate of change, okay, so if the rate of change of, let's say, z is based on y, and the rate of change of y is based on x, then we can find the rate of change of z based on x through y with the chain rule. And I like to draw a picture for this because in words it maybe isn't as clear as what I'm trying to get at. So if z is based on y, so let's say for z, z is the dependent variable for y. So its rate of change, right, it's based completely on y. But y itself is completely based on x. Okay? So z's rate of change can be completely determined by y, and y's rate of change can be completely determined by x. Well, it turns out that we can move through them, okay, to get dz dx by basically taking dz by dy and multiplying by dy dx. Okay, now here's an example I like to use to sort of explain what's going on here. Okay, I like to use Mario Kart. Of course, you can use any sort of racing game or whatever. It doesn't matter that much. But I like Mario Kart because I can say, let's say we're talking about 3 racers in Mario Kart. So 3 racers in Mario Kart. Let's say Toad, Bowser, and of course Mario. Okay, so let's say Toad drives 3 times faster than Mario. Okay, so that means Toad's velocity in relation to Mario is 3. Okay, in other words, I could say that the derivative of, or the rate of change, derivative of Toad's driving in relation to Mario's driving is 3, right? How they compare is a factor of 3. All right, further, then suppose Mario drives twice as fast as Bowser. So, which kind of makes sense, Bowser, bigger dude, drives a little slower. So in a similar fashion here, that means Mario's velocity in relation to Bowser's is a factor of 2. Okay? So in other words, I could say that dm by db is equal to, that should be a 2, or Mario's velocity in relation to Bowser's is 2. So remember what a derivative does. It tells us how one quantity is changing in relation to another. Well, if Mario's always driving twice as fast as Bowser, his rate of change compared to Bowser's is always a factor of 2. So in other words, if Bowser drives at, let's say, 100 miles an hour, Mario's going at 200 miles an hour. Okay, just as a quick calculation there. So, finally, given this, since Toad drives 3 times faster than Mario, and Mario drives twice as fast as Bowser, from here we can say that Toad drives 6 times faster than Bowser. All right, and we can say that Toad drives 6 times faster than Bowser because, well, if we think about it in terms of a picture here, okay, so that Toad, of course, drives 3 times faster than Mario, who drives 2 times faster than Bowser. So if we jump straight to, or from Toad to Bowser, Toad is going to be 6 times faster than Bowser. So we can say that dt by db is 6, or that was, of course, 3 times 2, and the 3 was how fast Toad was in relation to Mario, and times the 2, which was how fast Mario was in terms of Bowser. So what we have here is going from Toad to Mario, that's dt by dm, and going from Mario to Bowser is dm by db, but going straight there is dt by db. These two things need to line up. Okay? And that is essentially how the chain rule works. This is a very goofy explanation of the chain rule. Okay? If z is related to y, which is then related to x, you can get from z to x either by doing dz by dy, then dy by dx, or trying to go straight there would be dz by dx. So from this, the dz by dx must equal, okay, the dz by dy times dy by dx. And it shouldn't be that surprising if you think about it in terms of these, say, dy's canceling. All we're doing is essentially, you can almost think of it as these dy's canceling to get us to here. Okay, that's essentially what the chain rule is doing. Now, the reason we have it is often this side of it is much easier to find than this side. All right, to put this in more general terms, if z is a function of y and y is a function of x, then the derivative of z with respect to x is the derivative of z with respect to y times the derivative of y with respect to x. Not much different here. All we're doing is this sort of same arrow through. The dz by dy times the dy by dx gives us the dz by dx. Okay. Another way that this can be written, though, right, is by saying this. If we want to find the derivative with respect to x of f of g of x, right, in this notation, it's going to be f prime of g of x times g prime of x. And this might not seem like the same thing, but if you drop the of x here, this is going to be f prime of g times g prime of x. In other words, df by dg times dg by dx. And here, if we, on this side, this is the df by dx. Okay, so it's sort of the same thing, just written a little differently in sort of the function notation. Okay, and I prefer writing it sort of this way with the f prime of g without the of x, because to me that really kind of tells me what we're doing. We're basically taking the derivative of the outside sort of function and leaving the inside function alone, okay, and then multiplying by the derivative of the inside. So this is often how I think of it instead. My sort of shorthand way of thinking about the chain rule. Okay, I think of it as the function f of some inside stuff. Okay, so the derivative of something like this, just a function with something on the inside that's not just x, is It's going to be f prime of the inside left alone times the derivative of the inside. Whatever that might be. Now that might be more chain rules, it might be product rules, it doesn't really matter. Or I often think of this as the derivative of x with respect to f of some stuff, right? The derivative of f of stuff is f prime of the stuff left alone. Then you just need to multiply by the derivative of the stuff. Okay? So what does this mean for us exactly? Well, we could leave things like this, or you could think that this just generalizes or advances the rules we already have. All right, so simply advances the rules we already have. So for example, if I want to take the derivative of, let's say, e to the stuff, right? Well, the derivative of e to the stuff, well, the derivative of e to the x is basically itself. So this is going to be itself, e to the stuff, times the derivative of the stuff. So I'm just going to put stuff prime here. Actually, maybe I should put the d by dx. Okay. So if I also want to do like the derivative of stuff to some power, let's say stuff to the 10th. Well, we're just going to differentiate this like normally, but we leave this stuff alone in the first step. So with our normal power rule, okay, it's going to be, we'll move the 10 down. We raise it to the 9, but I'm going to leave the inside alone. So it'll be 10 times the stuff left alone to the 9, then times the derivative of the stuff. Okay. What about cosine of stuff? Well, cosine of stuff, well, the derivative of cosine is negative sine. So it's going to be negative sine of the stuff left alone times the derivative of the stuff. Okay, so really all we're doing is taking the rules we already know, but giving them more opportunities to be more complicated. Okay, so let me show how I like to think of these rules, of course, that we already have, but advance with the chain rule. Okay, so most books like to use U for the stuff, right? And there's a reason for that we'll get into later. But you can use Y or Z or whatever. But yeah, the book uses U, so that's what I'll use here. So we have the power rule, right? So the power rule basically just says that the derivative with respect to x of x to some power is the power times x to the power minus 1. Well, now we can say that the general power rule, or you can think of it as the chained power rule, says that if you have the derivative with respect to x of u to the some power p, that's going to be p times u to the p minus 1 times u prime. In fact, all of our rules are going to be exactly the same. We just have to multiply by u prime. So they'll be the same with x as they are with u, except with u, since we're not differentiating by the same variable, we just need to throw in a u prime. So for example, the chained exponential rule, okay, the derivative with respect to x of e to the u is going to be just itself times u prime. All right, and notice we've been doing this the whole time with e to the stuff, because remember, the derivative with respect to x of e to the 2x is 2e to the 2x, but 2 is the derivative with respect to x of 2x, right? That's what that 2 is. We've been doing the chain rule for a long time now, we just maybe didn't realize it. Okay, so basically all of our rules can carry right over. Just if you have stuff on the inside, you've got to multiply by the derivative of that stuff. All right, so here are all of our rules that we know, like our basic rules that have now been chained, right? So we talked about the power rule, e to the stuff. Well, general power, b to the u, will be ln b times b to the u times u prime. Then for the trig functions, you'll notice I put the u prime out front instead of on the other side. Often with the trig functions, it just looks better that way. It doesn't really matter. But yeah, sine of u will be u prime times cosine u. Derivative of cosine u will give us negative u prime times sine u. Derivative of tangent u will be u prime times secant squared u. Derivative of secant u is u prime times secant u tangent u. Derivative of cosecant u is negative u prime cosecant u cotangent u. And finally, the derivative with respect to x of cotangent u is equal to negative u prime cosecant squared u. A question I get a lot is, when do you use the chain rule? Okay, and the answer is essentially always. Okay, we always use it. You might not even realize it. For example, the derivative with respect to x of, say, x squared. You could think of this as stuff squared. So you do 2 times the stuff left alone raised to the 1 times the derivative with respect to x of the inside. Well, the derivative of the inside here is just 1. So we get 2x. We're always doing the chain rule. It's just if the inside function is just x, we don't really bother, okay? So that's always my quick answer, is just always do the chain rule, okay? Eventually you'll start to get the hang of the fact that, oh, okay, if it's just x on the inside, I don't have to worry about it. But if it's some other stuff, then we do. All right, now we're just going to roll through some examples, all right? I think now that we've got that out of the way, I think just seeing a bunch of examples is what's going to help the most. So here, this is our u on the inside. So technically this is u to the 10th that we're looking at, or you can think about it as stuff to the 10th power. Okay, so when we do our derivative, remember it's going to be, if this is u to the 10th, the derivative is going to be 10u to the 9th times u prime. Okay, now while you're still learning this, it's probably not a terrible idea to write this out every time, okay, to try and get the hang of it. So this will be 10 times u left alone. Okay, so that's going to be, actually let me leave it in white here. Okay, so here's 10u, so this is still u left alone, then times u prime. So u prime is going to be 6x plus 7. So this right here is our u prime. All right, so we could now just simplify this if we want. We could move this out front, and then multiply it by the 10. We don't have to. We can leave it like this. I'm going to leave it like this for a second, just to show that this is how you can leave your answer if you want. But probably the furthest way you could simplify this is distribute the 10 through to give you 60x plus 70 times 3x squared plus 7x raised to the 9th. But again, I tend to just leave it at this step here. All right, next up, let's say we have the square root of 10x plus 1. So there's one that we didn't put in our basic one, mainly because it's a generalization of the power rule. But so if we have the square root of u, derivative of square root of u is going to be 1 over 2 root u times u prime. Okay, or u prime over 2 root u. Okay, so in here, this 10x plus 1 is our u. Okay, so u prime, or sorry, y prime is going to be u prime. So that's going to be 10 on the top, all over 2 times the square root of u. So this thing left alone. Okay, so notice that this is still u left alone. And the 10 and the 2 will cancel to give us 5 over the square root of 10x plus 1. Of course, if you don't want to do it that way, you could always just rewrite this as 10x plus 1 to the 1/2 power. And then your derivative would be, instead, we still have the same u, of course, but now we're using a power rule. So it'll be 1/2 times 10x plus 1 to the negative 1/2, then times the derivative of the inside. So this is u still left alone, and this is u prime. I guess I should have written here that that 10 is u prime. Okay, and that simplifies out to be 5 times 10x plus 1 to the negative 1/2. And guess what? If you move that down into the bottom of the fraction and change it back to a square root, you get the same thing. So it doesn't matter which way you go here. You'll get the same answer either way. All right, next up, let's say y is equal to 5 times 7x cubed plus 1 all to the negative 3. Okay, so in this case, this is our u, and we're looking at essentially 5u to the negative 3. Okay, so when we differentiate, we're going to bring that negative 3 down. Okay, so that we always do. So we're going to have a negative 15 times the u stuff left alone. So notice most derivative rules have stuff left alone, right? Product rule, quotient rule, chain rule. And then negative 3 minus 1, which will be negative 4. So I did this in a different color here to show that we're basically differentiating the outside stuff. We leave the inside stuff alone, and then we multiply by the derivative of the inside. So in this case, that's going to be 21x squared. So this is our u prime. Okay, so essentially what we have is negative 15 u to the negative 4 times u prime. That's what our derivative ends up being. So to simplify it a little bit, we could bring these two things together. All right, to get negative 315x squared times 7x cubed plus 1 to the negative 4. Okay, so there we go. There's our chain rule derivative. All right, next up, let's look at secant of 3x plus 1. So here's a place where it's easy to mess up, okay? So remember, the derivative of secant of stuff, so secant of u, is going to be u prime secant of u tangent of u. So the u part is going to be listed twice. So this 3x plus 1 is our u, okay? So when we do y prime, it's going to be u prime. Well, u prime is going to be 3. Okay? Then it's going to be secant u, which is 3x plus 1, times tangent of u, 3x plus 1. Okay, so in both cases here, this is a u, and this is a u. Okay, and the derivative, this is u prime, is just 3 in this case. But the final answer, just to write it in a less cluttered form, is 3 secant of 3x plus 1 tangent of 3x plus 1. Okay, so be really careful with the secant and cosecant. That lists the secant or cosecant, tangent, cotangent twice. Make sure you put the u part twice as well. If you need to go back to the u's to do it right, there's nothing wrong with that. Okay, it's always okay to write more than less if it helps you get to the right answer. All right, next up, I want to show that this is how the book writes this problem. And I do find myself kind of frustrated with how the book is laissez-faire with parentheses. In a way, I get it. But remember, the trig functions and natural log and functions like that always have an input. This is not a product rule. Okay, this is a chain rule because what it's saying is tangent of e to the x. If it was a product rule, it would be tangent x e to the x, because here you could fit in a times. So here it would be tangent of x. I know it can be confusing. So essentially, whatever comes right after the tangent, if they don't put parentheses, is the input. Okay, so if it's listed like this, what it's actually saying is tangent of e to the x. I don't particularly like how it does that. On the other hand, though, as you go further in your math careers or physics or whatever, people abuse notation really abuse notation. So it's probably good to start getting a handle on these sort of things. But yeah, I don't particularly like it when we're still learning. But anyway, this is tangent u, right? Tangent of stuff. So the derivative there is going to be u prime secant squared u. Okay, well here our stuff, thankfully, is e to the x. And I say thankfully because the derivative of e to the x is just itself, e to the x. And then it will be secant squared of u, which is e to the x. So here's our u, and here's our u prime. Okay, but our answer is simply e to the x times secant squared of e to the x. All right, next up, let's look at sine of 4x cubed plus 3x plus 1. All right, I'm just going to jump straight to it. I'm going to take the derivative of the stuff. All right, that's going to be 4x, sorry, wrong. It's going to be 12x squared plus 3. All right, so if this here is our stuff, this is u prime, then it's going to be, well, the derivative of sine of stuff is going to be cosine of that stuff. Right, so it's basically cosine of the stuff left alone times the derivative of the stuff. In other words, up here, the derivative of sine of u is u prime cosine u. So that's what we have here. Here's our u prime, here's our cosine u. Right? Here's an example of exactly why the chain rule is invented, because trying to do this without knowing the chain rule, it's rather difficult because we can't really apply the product rule or any other rule. The same goes for like the sines and the cosines and all that kind of stuff, but this is one with a power that kind of falls apart if you try to approach it with the product rule. But as is, our u, or stuff on the inside, is 5x plus 1. It's just raised to a power, so y prime is going to be, well, we'll just move the power down 2/3. We'll leave the inside stuff alone, 5x plus 1, and then raise it to the original power minus 1. So 2/3 minus 1, which is 3/3, is negative 1/3. So this will be to the negative 1/3. Then we just multiply by u prime, which will be 5. Okay, so our u is left alone. and we multiply by u prime. So simplifying this a bit, we're going to get 10/3 times 5x plus 1 to the negative 1/3. And, eventually we'll be able to do this much faster, okay? And no problem if you're already at that point. But again, there's plenty you can write to help you through it stage by stage, step by step. All right, next up, this one's kind of nasty. This is the 4th root of 2x over 4x minus 3. Okay, well, first of all, we don't have a nice cheeky version of the 4th root. Okay, that's all right. We could just rewrite this as 2x over 4x minus 3 all to the 1/4. Okay, so now our u is, or our stuff is this 2x all over 4x minus 3. Okay, so it's basically stuff to the 1/4, right? So we're going to bring the 1/4 down, okay, and then subtract by 1. So y prime will be 1/4 times the stuff left alone. So always remember that. The inside stuff is left alone in the inside. You don't ever mess with that. Then it'll be 1/4 minus 1. That will be negative 3/4. And then here, we need to put the derivative of the stuff, right? U prime goes here. Well, u prime is going to be a quotient rule. So this is a quotient rule within a chain rule. However, notice I didn't even worry about that until I got to this step. I just was focusing on, oh, this is stuff to a power. So let's move that power down, raise it to the negative, like the power minus 1. And now I'm going to worry about the derivative of the inside, which is a quotient rule. Okay, it's going to be the derivative of the top times the bottom left alone minus the top left alone times the derivative of the bottom, which will be 4, all over the denominator squared. Okay, and hopefully you can kind of see that this is going to simplify a little bit. It's not necessary to do it, but I'm going to get an 8x minus 6 minus 8x. So it's just the negative 6 that's going to be left over. So we could say that this is 1/4 times 2x all over 4x minus 3 to the negative 3/4 times negative 6 all over 4x minus 3 squared. And yes, we could continue simplifying this or what have you. I wouldn't bother. This is good enough. All right, so for this next one, let's say y is equal to secant x plus tangent x, all raised to the 5th. Well, this is stuff to the 5th. All right, this is our u, and it's being raised to the 5th. So what we're going to do is bring the 5 down to get y prime is 5 times the stuff left alone, all raised to the 5 minus 1, which is 4, and then we will multiply by the derivative of the inside. And notice, when I do this, I don't really think much about what's on the inside until I need to differentiate it. So now it's, okay, derivative of secant, which will be secant x tangent x. All right, then plus the derivative of tangent, which will be secant squared x. Okay, so we can leave it like this. We could factor out a secant. I would just leave it like this, honestly. Okay. Of course, yeah, I would just leave it like this. All right, so for this one, let's say y is equal to the square root of 1 plus cotangent squared of x. Now, this one, of course, looks like a chain rule, but as I mentioned before, if you're on the lookout for your algebra or your trig identities, you can actually simplify this to not need it. right? Because if we start with our sine squared x plus cosine squared x equal to 1, we have other Pythagorean identities. And if you can't remember them, just divide by the right thing, right? If I divide this by sine squared x everywhere, we get, well, 1 plus, well, cosine over sine, that's cotangent squared. And then 1 over sine squared is cosecant squared x. So this is the cotangent cosecant version of the Pythagorean identity, which, you know, it's one that it's good to know, but if you don't, you can always get to it from the original one. So this thing actually equals cosecant squared x. So this is the square root of cosecant squared x, okay, which is just really just cosecant. Okay, and technically it's the absolute value of cosecant, so really you're just looking at where this would be positive. So, you know, that would simplify our lives a lot, but I do want to show how we would approach this if we did use the chain rule. All right, so using the chain rule, of course, it would be, we have the square root of u, essentially. So it's u prime over 2 square root u, or we could do this as the 1/2 power. Now, something to keep in mind though, the 1 plus cotangent squared x, this is the same thing as writing 1 plus cotangent x all squared. Okay, so whenever you have the cotangent squared x, so we can either think of this as a product rule within a chain rule or a chain rule within a chain rule. All right, so when we go to differentiate, it'll be u prime. Well, here's our u. So it's going to be 2 cotangent x to the 1 times the derivative of cotangent, which is negative cosecant squared. Okay, all over 2 times the square root of the stuff. All right, once we do that derivative part, the rest of it is pretty much baked in. Okay, so the 2's will cancel, and we have a lot of other cancellations. So we can still get to the answer even if we didn't recognize some of the things we could do to simplify the problem. Okay, I still wanted to show how to get there just using the chain rule. Okay, now here is an example of a chain rule within a chain rule, because if this is our stuff is already sine of stuff. So we have sine of some stuff, and that stuff is sine of some more stuff. Okay, but again, we just take it step by step, right? It's the derivative of sine of stuff is going to be cosine of that stuff left alone. Okay, then times the derivative of the stuff. Right, so here I want to put the derivative of the stuff, but the derivative of this is going to be another chain rule. So this is sine of stuff. Okay, so it's going to be cosine of the inside left alone times the derivative of the stuff, which thankfully is just itself. Okay, if you're having trouble following that, what I recommend doing is notice how I called this here u, and then we could call this v. So this is sine of u, and u is sine of v. Okay, so when we go through y being sine of u, y prime is going to be cosine of u times u prime. All right, then if we go up here, u prime is going to be cosine of v times v prime, using the chain rule again. So if we put that in here for our u prime, right, this will be cosine of u times u prime, which we just found is cosine of v times v prime. Well, now we can just put all this stuff in because our v, I didn't really write it, but our v was e to the x. So v prime is e to the x. So now we just put all our stuff back in. Cosine u, well, u was sine of e to the x. Cosine v, well, v is e to the x times v prime, which is e to the x. Okay, so you can always go back to u's and v's and w's or what have you to get to an answer if you have a really complicated mix of chain rules. All right, next up, we have another chain rule within a chain rule within a chain rule, essentially. Sine squared of e to the 3x plus 1. So I'm going to rewrite this as sine of e to the 3x plus 1 all squared. Right, because think of it this way. If I say that this is u, okay, we have y equals sine squared of u. But sine squared is already sine squared. So we can think of this, let's call this v. Okay, so this is essentially v squared. Okay, so the derivative of y is going to be 2 times v to the 1, okay, then times v prime. I should probably be very careful about that, huh? So that doesn't look like a prime. So 2v to the 1 times v prime. Okay, well, v is sine of u. So v prime is cosine of u times u prime. So now we'll put that in. We have 2v. I'm going to drop the to the 1 power because that's not really necessary. Times now cosine u times u prime. Okay, so what was u? Well, u is e to the 3x plus 1. Okay, so let's put that in. We'll have 2 times our v times our cosine of u, but our u was e to the 3x plus 1. And our u prime, well, if u is e to the 3x plus 1, then u prime is going to be 3e to the 3x plus 1, because it's just a basic chain rule here. The derivative of 3x plus 1 is 3. So u prime is 3e to the 3x plus 1. And let me, sorry, we're getting a little cluttered there. And now finally, I can replace this v with sine u and u with, in fact, maybe I should have done that already. V is sine u, and u is 3x plus e to the 3x plus 1. Okay, so finally y prime will be 2 sine u was e to the 3x plus 1, cosine of e to the 3x plus 1, all times 3 times e to the 3x plus 1. So you can move that to the other side here to give us that y prime is 6 e to the 3x plus 1 sine of e to the 3x plus 1 times cosine of e to the 3x plus 1. Whew. Okay, yeah, kind of a hassle, but if you don't see right off the bat how to approach these, you can always set up chains of u's and v's and w's and what have you to get down to your final answer. Alright, so I'm going to go ahead and put a cut in this video and come back in a part 2 where I'll just do a lot more examples. I think the more examples you see of this kind of stuff, the more familiar you'll get with it, the better off you'll be. So look forward to part 2 where we will continue to do more examples where we start mixing chain rules with product rules and quotient rules and whatnot. Alright, so I'll see you on that one. Cheers.